These are the notes for AP Calculus on the topic of limits with factorials and exponentials. So let's first review factorials, and recall that when you have an exclamation point like this with a number in front of it, it doesn't mean 5, although you could say it loudly if you really want to. Exclamation point in math means something different than what it means in English. It means you start with that number, and then if it's 5, you keep reducing it by 1. So 1 less than 5 would be 4, and you multiply these together. And then you reduce it by another one, so n minus 2 is 2 less than 5 would be 3. And you keep multiplying these together. Until you get down, you always stop at 1. These are used in a lot of different problems involving probability, combinations, permutations, as well as other applications. It's just a compact way of writing this. Starting with that integer and counting down all the way to 1. In this case, if you multiply those together, notice this would be 5 times 4 is 20, 3 times 2 is 6, 6 times 20 would be 120. So 5 factorial is the same as 120, just a different way of writing it there. So keep that in mind as we find some limits, some of which will involve factorials. Okay, so let's start with this one, and we're finding the limit as n approaches infinity. So remember, first thing to do is try to substitute in the infinity. However, on a lot of these, there's some simplifying we can do first. It makes it a little easier rather than trying to plug in infinity right off the bat. So notice we've got 4 to the n plus 1 and 4 to the n. So let's focus on those two first. Well, when you have this common base, a simpler example would be if you had like x to the 8th over x to the 7th. Well, that would simplify to be x to the 1st. You just subtracted the exponents, right? The same thing happens here. The same base of 4, you have n plus 1 and n, which is 1 less than it. So one way of looking at it would be take n plus 1, that exponent, like the 8, and subtract n. And see that n's would cancel out, you just get an exponent of 1. So that's one way to see why this simplifies. So we're still right, the limit as n approaches infinity could just be 4 to the 1st, or just 4 on your numerator. Or if you put in specific numbers, you can see that it works also. If you had n plus 1 is 1 more than n, right? So if you had 4 to the 6th divided by 4 to the 5th, you can see, well, you'd subtract that would just be 4 to the first power. We have it. Now let's look at the n and the n plus 1. Let's see, could those be reduced or not? Oops. Sorry about that. So we've got n and n plus 1. So that would be, again, n plus 1 is 1 more than n. Let's say we had 6 over 7. Could that be reduced at all? No. So it's 1 more than the denominator if we had 10 over 11. Notice 1 more than that, that doesn't reduce, right? So the n and n plus 1, those don't reduce. So we'll leave that. And really this just becomes one fraction. I put the two separate fractions because a lot of times later on, when we go over some series that involve these limits, they'll be written as two separate fractions multiplied together to start with. So it's just getting used to that format there. So we have 4 to the n over n plus 1. So we simplified it first. Now let's go ahead and substitute infinity to help us analyze it. So we'd have 4 times infinity over infinity plus 1, but the plus 1 is negligible here compared to infinity. So we just plug it in there. And then you can see the infinities reduce out. And this would just give you 4. All right, let's look at a few more here. This is a little more complicated. So again, let's start by simplifying this as much as we can before we substitute in the infinity. So let's analyze again the 7 to the n plus 1. And notice here, 7 to the n plus 2. So here, notice n plus 2 is 1 more than n plus 1. So again, you could subtract the exponents. You start with the 1 in the numerator, n plus 2 minus n plus 1. That'd be n plus 2 minus n minus 1. The n's cancel out, you get 2 minus 1, which is 1. The only difference is the larger exponent's on the denominator, so when you simplify that, the 7 to the first power is going to be on the denominator. So we'll still have the limit as n approaches infinity. And now that 7 to the first is going to be on the denominator. Then n plus 4 and n plus 5. Again, n plus 5 is 1 more than n plus 4. So that'd be like if you had 8 over 9. So that doesn't reduce at all, so those would stay. N plus 4, n plus 5. And now let's focus on the factorial parts and see if those reduce at all. So we've got n plus 1 factorial and n factorial. So again, n plus 1 is 1 more than n. So let's look at a specific number so it's easier to see. So let's say n was 4. So let's say we had 5 factorial divided by 4 factorial. Well, that's simplified. 5 factorial would be 5 times 4 times 3 times 2 times 1. 4 factorial would start with 4 times 3 times 2 times 1. And then notice what we reduce here. For the 4 divided by 4 is 1, 3 divided by 3, 2 divided by 2. So all that's left is 5 on the numerator. Notice not even factorial. So when it's factorial, since this is 1 more than this, in general, this would just be left with n plus 1, would be what's left on the numerator. Notice that just this number, not even factorial. Just like the 5 is left over here. So now we can substitute infinity. That's as far as it simplifies. So we substitute infinity. We get infinity plus 4, where the plus 4 is negligible, so it'd be infinity, times infinity plus 1. Again, the plus 1 is negligible, so it'd just be times infinity, divided by 7, times the plus 5 is negligible when you plug in infinity, so times infinity. See, sorry about that. So we get infinity squared over 7 infinity. So one of those infinities reduce out there. So we get infinity divided by 7. But that's infinity, huge number divided by 7, it still goes to infinity. Remember, when you have infinities left on the numerator, there's two options, either positive infinity or negative infinity. In this case, it's positive. Okay, let's take a look at a couple more. All right. So on this one, we have square root of n plus 1 and square root of n, and n plus 1 factorial and n plus 2 factorial. Let's focus on the factorial ones first. And as this time, n plus 2 is 1 more than n plus 1. So if we look at a specific example, let's say n plus 1 was 6, for instance. Sorry about that. So if we had 6 factorial, n plus 2 would be one more than n plus 1, so that'd be 7 factorial. Oops. Sorry about that. I keep popping up all these programs unintentionally here. There we go. So 6 factorial would be 6 times 5 times 4 times 3 times 2 times 1. 7 factorial, 7 times 6 times 5 times 4 times 3 times 2 times 1. So notice a similar thing happens. Everything here, 6 is reduced out, 5 is reduced out, 4 is reduced, all these reduced to be 1. The only thing left is the 7, the one that's 1 bigger. In this case, that's n plus 2, that's 1 larger. So when you simplify this, we still have the limit as n approaches infinity. All that's going to be left of those is just the n plus 2 on the denominator. And then they've got n plus 1 square root and then square root of n. So again, let's take a look and see if that would simplify at all. By putting in specific numbers. So let's say n was 5. So we'd have the square root of 5. And then this would be one more than that, so the square root of 6. See how that wouldn't simplify at all? So there's nothing we can do with that. So that just stays square root of n plus 1 over square root of n. And then let's go ahead and substitute infinity and see what this simplifies to be. So we'd end up having the square root of infinity divided by, the plus 2 here is negligible, so just infinity times the square root of infinity. You could combine these, or just notice right here, the square root of infinities were reduced out. Oops. Sorry about that. Keep accidentally opening these other programs here. So these reduce out, and notice what's left this time is an infinity on the denominator. And when that happens, when you have 1 over some huge number, infinity, that's really, really close to 0. So this one, limit would equal 0. And all these limits, in case you're wondering why we're doing these like this with n instead of x, these are kind of building up to things we'll do later on in the year with series, just to get you a little more comfortable working with these, and simplifying these will make it easier when we incorporate these in certain series problems later on. All right, let's take a look at one more. All right, so let's see if anything simplifies here. Notice we've got e to the 2n plus 2 versus e to the 2n. So we got the same base. So let's apply that same principle we've been doing. Remember how we subtracted the exponents? So if we take the larger one, 2n plus 2 minus 2n, the smaller one. Notice the 2n's reduce out. Oops. 2n's reduce out, we're just left with 2. So what's left here is an exponent of 2, so we end up with e squared on the denominator, since that's where it's larger. So we have the limit as n approaches infinity. That part will just be e squared on the denominator. And then n plus 1 squared versus n squared. See if that would simplify at all. Again, let's say n was 4. N was 4, we'd have 4 squared. And n plus 1, that would be like 5 squared. Notice how that wouldn't simplify at all. So neither can this. So again, once you get used to these, you'll be able to simplify without having to do the specific numbers. But when you first start seeing these, to see whether it does or doesn't simplify, sometimes it's easier to look at with specific numbers rather than just in general with n. So n plus 1 squared Sorry about that. Doesn't simplify, and neither does the n squared. And then when we substitute infinity, well, the plus 1 is negligible here, so we get infinity squared divided by e squared and infinity squared. So you can see the infinity squared reduce out, and we're just left with 1 over e squared. So that would be our limit. And that concludes the notes for AP Calculus on the topic of limits with factorials and exponentials.